Welcome to the final installment of our Volcano series, the definitive masterclass that unpacks every facet of volcanic science. We begin by traveling back 4.5 billion years, when Earth's molten mantle first began to solidify, trapping heat and creating the earliest basaltic eruptions that forged the oceanic crust. Those primordial blasts set a template for the complex volcanic cycles we see today, and they remind us why some regions remain perpetually restless while others have quieted into geological dormancy. /n. Next, we explore the engine of volcanism, plate tectonics. At divergent boundaries, plates pull apart, allowing basaltic magma to rise in a process called decompression melting. This fuels the endless creation of new seafloor at mid-ocean ridges, a process measured in centimeters per year yet responsible for the majority of Earth's volcanic output. At convergent margins, one plate plunges beneath another, introducing water into the mantle wedge and triggering flux melting. The resulting magmas are more silica-rich, trapping gases that can lead to the explosive eruptions that define the Pacific Ring of Fire. Finally, intraplate hotspots like the Hawaiian plume tap deep mantle sources, producing fluid lava that builds the iconic shield volcanoes we associate with tropical paradises. /n. Understanding eruption mechanics is essential to grasping why some volcanoes flow gently while others erupt violently. Effusive eruptions, typified by Iceland's basaltic lava fields, produce low-viscosity magma that spreads over kilometers, forming broad, gently sloping landforms. In contrast, the high viscosity of rhyolitic magma at places like Yellowstone can trap volatiles, building pressure until an explosive Plinian eruption blasts ash and pumice high into the stratosphere. The dynamics of conduit pressure, magma-water interaction, and vent geometry dictate whether a volcano will favor lava flows or pyroclastic cloud formation. Each mode carries distinct hazards, from lava inundation to ash fall that can choke engines and alter climate. /n. History offers dramatic case studies. Mount Vesuvius, in AD 79, unleashed a pyroclastic surge that entombed Pompeii, preserving a Roman city in volcanic ash for centuries. The 1815 eruption of Tambora ejected 160 cubic kilometers of tephra, plunging the northern hemisphere into a year of abnormal cold, crop failures, and famine, a stark reminder of volcanic climate forcing. Krakatoa's 1883 explosion generated a 30-minute thunderclap heard across the Indian Ocean and injected enough sulfur dioxide to create vivid sunsets worldwide. More recently, Geological's ash cloud in 2010 forced the cancellation of thousands of flights, demonstrating how even modest eruptions can cripple modern infrastructure. /n. Scientists still debate the predictability of catastrophic eruptions. Seismologists argue that low-frequency tremor and harmonic tremor indicate magma movement, while geochemists point to rapid increases in SO2 as the most reliable precursor. Others contend that ground deformation measured by GPS and NSAR can capture subtle bulges in a volcano's flank weeks before an eruption. The origin of hotspots remains contentious. Is the Hawaiian plume a deep mantle upwelling rooted near the core mantle boundary, or does it arise from lithospheric thinning and localized melting? Meanwhile, climate researchers assess whether volcanic CO2 emissions, though substantial on geological timescales, can ever rival anthropogenic output, especially in the unlikely event of a supereruption. These interdisciplinary disputes fuel new technologies, collaborative field campaigns, and refined hazard models. /n. Looking ahead, the next decade promises transformative tools. Satellite radar interferometry now detects millimeter-scale deformation across remote volcanoes, feeding AI algorithms that flag anomalous patterns in near real-time. Swarm drones can map fumarole gases and plume composition without risking human lives. Communities are integrating these data streams into localized early warning systems, empowering residents with evacuation routes and shelter plans tailored to specific eruption scenarios. At the same time, engineers are investigating volcanic ash as a pozzolanic additive for cement, turning a dangerous byproduct into a sustainable building material. Finally, the lessons we learn on Earth are guiding planetary missions to Jupiter's moon Io, where active volcanism reshapes a world unlike any on our planet. By fusing cutting-edge science with public policy and innovation, we can mitigate risks while harnessing volcanoes as agents of change. /n. If this series gave you value, subscribe. More deep dives coming every week.